So it is important to tell you that or rather recall that in the last lecture we ended our discussion with the introduction of the subdifferential of a convex function f. So, f is convex and we defined something called the subdifferential of f at x. Of course, I am assuming the function is from Rn to R. So, this is f of so, this set is not always for a when f is from Rn to Rn, sorry Rn to R, then del of f at any x is not equal to phi for all x, and this is both convex and compact. So, it is convex, closed and bounded. So, these are the fundamental properties of the set valued map or the set which mimics the derivative at every point x where the function is not differentiable. And also I give you the homework to just check out that if f is differentiable, then differentiable at x, I would say, then this singleton set actually equals the subdifferential. That is, the subdifferential has only one subgradient and that is nothing but the gradient. So, these are few features of the subgradient you should know, and obviously the most important feature this is a necessary and sufficient condition for a point x to be a minimum of the function f over the whole set Rn. Of course, I now leave it to you as homework and I will put it up in the FAQs which will be in the course website, is that if f is not differentiable, in the not differentiable means okay, it does not have a derivative at every point, then if we minimize f over a closed convex set C, then what is the necessary and sufficient condition? That is your homework. So, those who can, they can check out it from my lectures on convex optimization in the same NPTEL series, then you will be able to figure out what is it, then what is the necessary and sufficient condition for optimality. And it is Also important to know that if I say that this is imitating the derivative, then this must be able to give me some calculus rules. So, it really gives me some calculus rules, but there will be one rule which differentiates this convex non differentiable calculus from the standard differential calculus that you know. So, it says that del of, if you have two convex functions, see here everything is convex. So, I am not writing convex convex, okay. If you want, I just write convex. I am giving you the most simplest, I am giving you all these in a more simpler descriptions. Actually, in more advanced texts, you have f from Rn to R bar. R bar is an extended real line which includes minus infinity and plus infinity. So, this set, sorry, computed at any x in Rn would now be same as the Minkowski sum of these sets. That is, any element here is the sum of one element here plus one element here. So, another calculus rule which is simple to understand, you take any lambda where lambda is greater than or equal to 0, then compute this function lambda f at x and then take the subdifferential. This is same as doing this. So, there is a sum rule like the derivative, there is this rule of getting the constant out, there is also a composition rule, but which is much more complicated. So, I will not talk about, but there is this rule about the max function which may be of interest. So, I just give you the formula rather than more detailed description. For that, you really have to go to the convex analysis course, convex optimization course. So, suppose you have a function f x and you see that here I assume that all these functions are convex and differentiable. All of them are convex and differentiable. Now, f is convex, but not differentiable. So, the standard composition rule, composition by some functional called max, is not applicable here. You cannot use the derivative. So, you need to compute the subdifferential of this. The subdifferential is actually computed in this way. First, you for a given point x, you construct this set J x, which consists of all the indexes I chosen from 1 to m, for which f of x, this function, equals to that f I x, because here I have a finite number of functions. So, once I plug in an x, at least one of them must be equal to this, because f x is the max value of among all this. So, once you know this particular set, this is nothing but compute the gradient of f I at x, collect those, compute the gradient of f I at x for those i's which belongs to this set J x. So, you do not compute for every function I. So, you reduce the computational effort once. So, given an x, a computer program can immediately recognize the set J x, and so for that you just have to consider for that x only those i's which belongs to J x, or your computational effort reduces, and then you have to collect those elements and take the convex hull. So, there are only finite number of elements. So, it will be a polyhedral set and a polyhedral compact set. So, give me any, I can definitely give me an x, and if the function is not differentiable at that point, right, that is when there will be at least more than one I, when Jx is more not just singleton, those are the points where the function is usually not differentiable. And then if you ask me to give me an element of the subgradient, a subgradient at that point as element of the subdifferential, I can use you very simply compute by using this formula. Of course, how would you really construct the convex hull to geometrically view it? That is a very difficult thing to do. You can use random methods and many exciting things can be done out of here, but from a computational point of view. But the interesting part is that it tells you that if you just want an element, I can give you an element, because this can be easily enumerated through a computer program even if this is large, and then immediately you can know which are the grad FIs you have to compute, and then you just compute an element of the convex hull. You choose anything, choose the lambda 1, lambda 2, lambda n in the way you want, and so make some random choice and you will get an element. So, you see this is a beautiful formula, and that is what makes convex analysis so powerful, and this convex non-smooth calculus so powerful. This has no analog in the smooth calculus or the standard differential calculus that you know, and one must also realize that the fact that non-smoothness or non-differentiability does not just arise out of the blue, it comes by taking the maximization of certain functions or minimization of certain functions. It typically arises in this form. So, then we really have a nice method, a constructive method to compute the subgradient, and that is why the subject is so beautiful and so powerful. So, I do not get into too much of details with convex issues, but let me go back to this so called projected gradient method that I had wrote down in the last lecture, that if I am to solve, minimize a convex function f x over a closed convex set x, then I know that x bar is a solution if and only if it is a projection on x of x bar minus alpha grad f x bar. Of course, I am assuming differentiability, where alpha is anything greater than 0. This is an if and only if condition. So, from this we said that okay, then we generated a iterative scheme So, you really have to choose a step length alpha carefully, projection on x, I wrote x there. So, this is called the projected gradient method, and we are going to today discuss why this works, and I want to tell you what happens if the function is not differentiable. Can you have a similar sort of formula for the, can you have a similar sort of necessary and sufficient optimality condition which would lead to a projected gradient method. So, which could be slow actually in practice might be, but mathematically would lead to a method which have a beautiful convergence, in the sense that under certain very simple conditions, all the sequence that you generate, any accumulation point of such a sequence is a solution of that convex programming problem, this one CP. So, it's important to have a look at this sort of formula, projection formula, because now these formulas are also used for much more different sort of problems with very special structures like SDP and other conic optimization problem. So, we want to discuss this one. So, you might ask me, why do you think that such a formula would work? How do you think that it will give us a solution? The idea could be very simply like this, that what happens in optimization is, suppose this is your constraint boundary, feasible set boundary, and this is your minima, unconstrained minima of the convex function, and just for the time being assume that these level sets are level sets, that is set of all x for which f x is some alpha, that is f x values are fixed, objective values. Now, this, so the minima, the constraint minima, because the function values are increasing in this direction. So, the constraint minima is here, so maybe x here, the constraint minima is here, this is x bar. But I may not be able to start with x bar immediately. So, this is your unconstrained minima, x hat, that is unconstrained minima. X bar is unconstrained minima, and you have to notice that these sets, these lines, which I have also called level sets, level lines, level curves. So, anything inside these is called level sets or lower level set. Okay, let me tell you something. Now, what would happen if I start from a point here? A level curve is also passing through this point naturally. So, this is x1. See here, the gradient of this function is always outward normal to this curve, to the level curve, gradient at that point to f. So, here again, if you want to find the gradient, it is actually here. So, if it is a gradient of f at x1. So, I am looking at the negative of the gradient, right. So, this is my x1, suppose, and from there I move in the direction of negative of the gradient. So, this is my up to certain distance alpha, like, so which is x1 minus alpha grad f x1, which you see have gone outside the set x, right, which is outside the set x, is this point, and from there I can draw a projection or a perpendicular on this set, that would give me x2. And with x2 I can do, for example, if the level curve is here, it is again the similar thing, again from here, which is x2 minus some alpha, this is alpha 1 I guess, so alpha 2 grad f x2, you drop this, you drew this and come like this towards the solution. So, this is the geometrical meaning of the projected gradient method. Now, once the geometrical meaning is settled, it is very important to tell you mathematically when and how this actually works, that the solutions that has generated would really give me the actual solution. So, I will now use some of my notes here to figure out why this method works, and after that I will keep you a question. Suppose I just consider a differentiable function over a closed convex set, I want to minimize just a differentiable function. Can I use the projected gradient method? Projected gradient means because you are projecting the gradient, which is obviously projecting the negative of the gradient in some sense. The gradient at a point negative of the gradient and projecting this. So, my question is, when does the projected gradient method works? So, let us make certain assumptions. Assume the convex problem CP. So, take this problem. So, where f is a convex function and x is a convex set. Fact, I think I should repeat because this is not really a convex optimization core. So, this is convex function and this is convex set. Now, I will assume that the function is of type C11, technically called C11, in the sense that the gradient function, which is a vector function, a function from Rn to Rn of f, is a Lipschitz function, Of course, this projected gradient method works for the case where you can have nice projections. So, I will give you tomorrow some cases where you can have very simple projection formulas, and for those cases which are also important in applications, this sort of method will actually work. Now, here so we will assume that the gradient of f has a nice behavior. Let us make a list of assumptions. Exists m greater than 0 such that for all x y in Rn. So, this is a nice behavior. I can give an example. Take a quadratic function, you will have this. Take a convex quadratic function, half x transpose A x, and this is immediately satisfied. And I urge you to find others. This result is due to Ruzinski. It appears in this book, I think I should mention it. It appears in this book, Nonlinear Optimization, published by Princeton University Press around 2007. Okay. This is m times norm of x minus y. So, this is something called the Lipschitz property. That the distance between the functional values and the distance between the original points has this relation. So, the distance between the functional values is less than some constant of the original point, right. If m is 1, then we call that map as a non-expansive map. B. Now, when we start an algorithm, we start with the point x1, and suppose that x1 is not the solution of the problem, and then we assume, then it is clear that the solution must lie in the following set. Let x1 in the is a starting point, let x1 is a starting vector, then assume This is a crucial assumption. In the picture that is actually happening, figure out why. You see X1 here, if it is a starting point, if it is not the, if it is a solution, fine, if it is not the solution, then the solution must lie in this set, because you are minimizing the level set of X1, Fx1. Now, if the solution is lying in this set, and if this set is compact, then I basically have to minimize the function over this set, and then if the function is, since the function is continuous, I will be able to pinpoint the minimizer, because the minimizer would exist, because this function is, this set is compact. This set is compact is guaranteeing that the minimizer is actually existing, right. And what we will do, we will generate iterates in this set, that any x2 must have the x2 should be in this set, x3 should be in this set, x4 should be in this set, and the accumulation point of that sequence would also be in this set, because this set is closed, and that would give us some insight. So, this is one major result, a major thing. Now, let the step size alpha. So, alpha here is called the step size, just like the line search method. Line search method, which will be xk minus alpha, this is something like a steepest gradient thing, but here you have the projection business. So, here, sorry, not there, this alpha is, I can always write as alpha k if you want. I can, this is called the line, it is called the step length as in the line search case. Now, let the step size alpha satisfy so many assumptions are there, and now we will prove. Now, if I have taken these assumptions, then let us see what happens. So, this is my convex problem CP. So, if these three assumptions hold, these are not very unnatural, quite natural. For example, they would be very useful in solving quadratic optimization problems. This can be very useful in solving a class of problems called the linear complementarity problems, where M is positive, where the matrix is positive semi-definite. We will not get into that, we will just give those examples afterwards, but here let me do something. Here let me try to come to the conclusion. So, if this happens, then any accumulation point or limit point of the iterates generated by the projection gradient method so you choose your alpha, step size should not exceed this quantity. Sorry, escape plus. That is, it is generated by the projected gradient method. if you do not know, again just okay, alpha has to be chosen by you, right. So, it would be alpha k. So, generated by this projected gradient method, then any accumulation point of the iterates generated by this is a solution of CP. So, this will generate an iterate sequence x1, x2, xk. So, this sequence xk actually will show lies here, because it is a compact set and this it will be a bounded sequence. When every sequence has a, in a compact set every sequence has a convergence subsequence. So, there will be a accumulation point which is a or a limit point. Okay, just forget about this word limit point, the limit may not exist, whatever. The limit exists, then it was limit points, if not accumulation point. It is better to write accumulation point. So, xk is bounded. So, there will be a convergence subsequence which we are not renaming, and it will go to some x star. So, that x star is a solution of CP. That x star is a solution of CP. So, our class today will end by justification of this fact. So, our class again I say that class today will end by justification of what we have said, which means giving the proof. So, let us see. So, we will start with some sort of integral, so called integral form of the mean value theorem. Very simple, nothing to, there is a standard formula. We will rub this part, we will work it out on this part also. There is a convex combination of these 2 points that will usually appear in the mean value thing, and there is a d theta here. So, what you essentially do is you add a term grad fxk inner product xk plus 1 minus fxk, that you add and subtract. So, I can write now that fxk plus 1 is f of xk, right, plus grad of fxk xk plus 1 minus xk. If I also add, I also have to subtract, and then I can put the whole thing down into the integral and write, I can subtract that part and now pull the whole thing into the integral, because I can write any constant into 1. So, 1 can be written as 0 to 1 integral d theta. So, I can write this as see the idea to write like this would be soon clear, that I can then use my Lipschitz property. So, basically when I add this term, I can pull it into the integral just by writing 1 equal to 0 to 1 integral d theta. This inner product d theta. Now, once you write down the I can write this as less than equal to norm of this, which is Cauchy-Schwarz. So, finally, I can use the Lipschitz property, which is up there, to write that this is less than fxk plus m times 0 to 1 theta norm x k plus 1 minus norm x k. This first norm would come, x k plus 1 minus norm x k would come from the Cauchy-Schwarz here, and then applying this rule, Lipschitz property here, m will come out here. And theta is of course the difference between this and this. So, it will be theta x k plus 1 minus x k, and that theta would come out and that is positive. So, it will just come out of the norm. So, that is what you get here. So, this will finally give me, of course, with this you have to add, of course, there is another term added to this whole thing. Maybe I should write, I should not forget this term. So, maybe I should write it in a better way. X k plus 0 to plus m times 0 to 1 theta norm x k plus 1 minus x k whole square d theta. So, this would give me that f of x k plus 1 is less than f of x k plus grad of f of x k plus 1 minus x k plus m times or m by 2 into, because theta square by 2. So, 0 to 1 integral, that is what you will get. So, let us keep this formula there and try to work out the things here. A part of which I will also encourage you to work out yourself rather than just following this proof, is to know that here we are working with this sort of projection So, this is what happened. Now, what does this mean? That this is the projection of this, but just by the definition of projection means, so this vector minus this vector is in the element of the normal cone. So, which means x k minus alpha grad f x k minus x k plus 1 into x k minus x k plus 1, this must be negative. Right. This is just from the definition of the normal cone. Think about normal cone. Okay. Now, this can be rearranged to write as, so you please do this, check out this calculation, and I am sure this calculation is correct. So, once you get this, now apply this star, apply this to estimate this thing here. So, that would give you sorry alpha. Now, because of this condition, sorry m by 2, what I am writing m by 2 is here. So, because of this condition this is positive. So, here you are actually this whole quantity is a negative quantity which you are subtracting. So, for each k, for whatever be your k, so this is there. So, if I call this set as S1, this set, then this sequence, this is a, so what you have generated that for every k, xk is a subset of S1, is in S1, and this sequence is a monotonically decreasing sequence starting from, this is true for all k in the set of natural numbers. So, k is equal to 1, fx1 is bigger than fx2, fx2 bigger than fx3 and so on. So, this is a convergent sequence. Right, this is a convergent sequence. This is a convergent sequence. So, this is decreasing and hence convergent. Obviously, this is all bounded below because of there is an infimum here and the infimum is achieved, because the infimum lies in this set and it is achieved, and that fx star value must be the lowest among all of them, and you are decreasing, you show there is a decreasing sequence which has a lower bound. So, it is convergent. So, it is a bounded sequence which is convergent. We are applying very basic real analysis. Now, once this is known, what do you have then? Then it is your job to prove from this equation that xk plus 1 minus xk, this norm is going to 0. Show. It is a very simple thing. If you know some bit of manipulation and can do a little bit of analysis, you can easily show from here that this result actually holds. So, if that result actually holds, that would simply tell you that limit k tends to infinity, projection C xk minus alpha grad fxk minus xk is equal to 0. Now, let x star be the accumulation point. So, let us take x star. So, xk is in S1 which is bounded. So, x star is accumulation point for xk, that is it is. So, there is a convergent subsequence in xk which goes to x star. Projection mapping, by the way, let me just tell you, because for a convex set every for a given point a projection point is unique. So, the projection mapping is a continuous function, it is a function which actually satisfies this sort of property Lipschitz with m equal to 1. So, the projection mapping is a continuous function, then by using continuity what I will have is projection j x star minus alpha grad, because f is convex function, it is a continuous, grad f is also continuous because of this Lipschitzian property. So, anyway it is continuous. So, a convex function which is continuous on the whole of Rn is a convex function which is differentiable on the whole of Rn is also continuously differentiable, but we also have this property here. So, this. So, ultimately we get this is equal to 0. What does this equation tells us? It tells us that x star must be same as the projection of j x star minus alpha grad f x star, where alpha is the Now, sorry, I should be also doing a little bit of more analysis. Here I should be putting alpha x k, because this alpha k would change with, if I fix the alpha, then I basically have got a solution, because this is the if and only if condition. But if I want to now put alpha as alpha k, then what I will have here is alpha k. Now here observe that alpha k has to be always within this limit, for whatever be your k, alpha k has to be within this limit. So, alpha k is a bounded sequence, and hence it will have a convergence sequence which goes to some alpha star, and that is the proper analysis. And here you have the alpha star, and so this would imply that I have found an alpha star which is greater than 0. Of course, alpha star is bounded, and we should have had the k, but for our simplicity of our discussion, alpha is fixed. So, if it is fixed, then I do not have to bother. Now, okay, I should put a question. Now, because I do not know what would happen, because there is strictly bigger than 0 here. Now, I put a question. If I want to vary the alpha in this scheme, here alpha is fixed, alpha greater than 0 is fixed, and alpha is between 1 by m and 0. So, now I want to say that how can I change alpha at every step. So, basically if I want to make a change here, then I have to make a change in this. So, instead of having this greater than just 0, I should have some number, say beta, which is strictly greater than 0, and it is here, and then it will be a bounded sequence, bounded between two positive quantities. So, their limits, its limit, it will be a bounded sequence so its limit cannot go beyond these two positive quantities. The limit has to be in the closed interval beta and 1 by m, and then you can push that and put an alpha star here. So, when I change the step size to alpha k, so we had worked with the step size constant fixed. Now, if I change the step size, at each step, can you repeat this? Can you repeat this argument? So, the homework would be to repeat this argument. So, let me just make a short summary. We start with this projection method where my alpha is fixed. If alpha is not fixed, then I have to do this. At every k, alpha k has to be chosen, then let the step size alpha k, or whatever alpha you choose, step size at each k, step size alpha k at each k satisfy this. Then you can actually run down this argument. You can have an alpha k here, and that alpha k will just zoom to some alpha star lying between beta and 1 by m, and then you will again have the same thing here with the alpha star, and that will again tell you that x star is a solution of CP. So, here I have, so again I want to assert, in our first starting, in the first write up, my alpha was fixed, then I am changing my alpha at every step, but keeping it, holding it between these two quantities, and then if that can be done, the whole argument can be repeated and you can reach the same conclusion. So, with this I end, and in the next class we will talk about penalty methods for solving nonlinear programming problems. Thank you very much.